at the Institute for Systems Research. Prakash is a founding member of the Maryland Hybrid Network Center. He has held several international visiting positions at leading institutions across Europe, Israel, and India. Prakash has also played significant roles in the IEEE Information Theory Society, including serving on its board of governors and so on. He's a fellow of the IEEE for his services to information theory and for his contributions to the field. So, round of applause.
Thank you very much. Thank you, Arvind and Bhardwaj, for your kind invitation.
Sure,
it's a pleasure to be back in contact with IIT Madras. And in fact, interestingly, in January, I was there for the 50th year reunion of my batch. So it's a pleasure. This talk, thank you very much for your kind invitation. This talk is on information theoretic data privacy, and it's based on joint work with Ajay Krishna Nageshwaran, who was a PhD student of mine who's graduated, and then Rohit Premlal, who's currently doing his PhD with me. And special thanks go to Himanshu Tyagi and Shun Watanabe, who introduced me to this problem area some years ago, and I still go to them from time to time to pick their brains. Now, the basic recoverability privacy setting that we're going to talk about is shown here. So there's a user, and the user is typically a database, let's say, possesses privileged information, and there's a querier. Querier is a server or a consumer of data, and it seeks a function of the user data. Now, the user provides in response what is called a query response, and that query response is usually a randomization of the user data through a privacy mechanism. And the user's query response must have the attribute that it enables the querier to recover the function value that the querier seeks with a specified accuracy. And this is usually called recoverability or utility, and we're going to refer to it as recoverability. At the same time, the user must ensure through the query response that the query response preserves privacy of the information of the user, and we'll make these notions precise as we go along. And the main questions that we seek to address are the following. What are appropriate measures of privacy and accuracy of function recoverability? What are privacy mechanisms that maximize privacy under this requirement of function recoverability? And what are the exact trade-offs between recoverability on the one hand, or accuracy, and the best privacy that can be obtained at the same time? There are many applications. First of all, just a few of them here. Individual user data must be protected when responses or query responses are released from a database, let's say, to queryers who seek information, for instance, on population level statistics. For instance, aggregate statistics of student grades or demographic information on students are released from a university database, and individual user data must be protected when this aggregate information is released. Or success rates of a clinical drug trial are provided by a hospital database. Or third-party applications request and receive social media user profiles and demographics, and individual user data should not be compromised. So the outline of the talk today is as follows. I'll start with data privacy, and the focus will be on data row privacy, and I'll allude to predicate privacy, list privacy, anti-collision privacy, and linkage privacy, which are all connected to privacy, data privacy in one form or the other. And then, of course, today's reigning approach in privacy is differential privacy, and a slight variation of it, which is called local differential privacy. I'll talk about it and say how we can link our approach to DP and LDP. Those are the abbreviations I'll use. Then I'll discuss distribution privacy, which is a new form of privacy, and we'll present an approach. I want to say here that ours is a new and it's a different. You can view our approach as a new and different approach, and it's a companion to the current privacy approach that is based on differential privacy. and it's based on first principles, as you'll see. So let me start with data privacy. Here's the model. So a user has data, which I'm going to model as a by random variable capital X, which is script X valued, and the cardinality of the data set, let's say, is R. Now, I should mention here that the data set can be multidimensional. And then there is a querier who seeks a function of the user data, and that function is given by a mapping F, which goes from X to Z. Z, just let's say, is the set 0 through k minus 1. So the cardinality of Z, the function values, set of function values is k, and of course, k will be less than or equal to R. Now, the user provides a query response, which is in effect a randomized version of the data. So I'm going to call it capital F, also denoted by Z equivalently. Now, this randomization can be also represented equivalently by a stochastic matrix, which goes from the data set X to the function value set Z. It's a stochastic matrix, which means there are as many rows as there are elements in the data set. There are as many columns as there are function values, and every row of the stochastic matrix is going to be a probability mass function. Now, as I said, the data set X can be multidimensional. For instance, if it's a vector of size D corresponding to D users whose data is hosted by a database, then we can fashion F to describe demographic variable counts of X, for instance, gender specifics, age brackets, geographical locations, etc. Throughout, we're going to assume that X has a known probability mass function Px, and then the user devises the query response f of X, which again is a randomized version of X, in such a way that a recoverability condition is satisfied. And that recoverability condition is the following: that given a value of rho, where rho lies between 0 and 1, the query response QR, I'm going to abbreviate it by QR, which is f of X, must satisfy the following recoverability condition, namely that the probability that f of X, the query response, equals a function value, little f of X, for every value of the data X equal to little x must be bigger than equal to rho. And this must be true for all data values. It's a stringent requirement. And this, as I said earlier, can be represented also by a stochastic matrix W, which goes from X to Z. So this is a stochastic matrix. And the stochastic matrix must have the property that if I look at W of f of X, that's the function value corresponding to the data X, this must be bigger than or equal to rho, again, for every value of X in the data set. Now, as I said before, I'm going to interchangeably represent the query response f of X also by Z. And I'll be flipping back and forth between these two, between this notation. Now, such a query response, so f of X or equivalently W, will be called rho recoverable or a rho QR, and this is the terminology I'm going to use. Now, the thing to note here is that the rho QR, the query response, is chosen by the user. Okay, next we go to the notion of data privacy, and here's one notion of data privacy. So data privacy is defined for us in the following way. So privacy, the privacy of a given rho QR F, which is also the same as W in terms of representation, is going to be denoted by pi sub rho of F, which is also pi sub rho of W. And this is going to be, we look at the probability that the querier forms an estimate based on the query response of the data value, and we look at the probability of error, and we'd like to minimize this over all choices look at the minimum probability of error for the querier over all choices of estimators. So these are all estimators of X, and this is done by the query. Again, this f of X will also be equal to Z, and this, of course, we know the probability of error is minimized by the maximum a posteriori estimator of X on the basis of the query response. So this is going to be the probability of the map estimator making an error. So f of X not equal to X. Okay. So this is the map estimator, and this is the map estimator of X on the basis of the query response f of X or Z. Now, what is data privacy? Data row privacy is defined as follows. Again, a row is the level of function recoverability that the querier demands. The data privacy is defined for a given value of row. Row is any value between 0 and 1. 1 means that the querier knows the full function value. 0 means no information is provided in effect by the user to the querier. And this is going to be defined to be the maximum privacy attainable by any row QR. By any row QR. And that's going to be the maximum of the term we defined earlier by row of W over all stochastic matrices W that represent query responses that satisfy the recoverability condition. So W of F for X, given X must be bigger than or equal to rho for all X in the data set. And the question we seek to answer, for starters, is to characterize this row data privacy. Let me put it this way, characterize phi data of row for every row lying between 0 and 1 as a function of row. And this represents, in effect, the best utility privacy trade-off. All right, now, that's the first question. The second question is devise privacy mechanisms that attain this best trade-off. So that attain phi data of row. So let me ask, is this coming across clearly? Can you hear me?
Yes.
Okay. Yeah, it's good. So are there any questions?
And can you view what's going on the screen?
Yeah, we can see the screen. So I had a basic question. So here little f is deterministic, no?
Yeah, little x is deterministic, right?
I mean, you can modify all definitions to also include randomized functions, little f.
I'm sorry, so I can't hear you. What is that again?
You can modify all definitions to also include randomized functions, little f, or maybe that's not required. Or
randomized functions of the data, you mean?
Of the data, yeah.
Yeah, so in fact, that's what we are doing, right? So at this point, the function value that the query seeks is a deterministic function. Yeah. And so that's what the function value the query wants to know. And then the user randomizes the data through this mapping capital F, which can also be viewed as a stochastic matrix. So this is general enough to capture randomization of the query response.
No, I was referring to randomization of the original function little f, but I guess that is also.
Yeah, sure. Yeah. No. The thing is, you can. There are many ways of doing it. The user, as you'll see, the user can take the data and directly randomize it, or the user can take the function value and randomize it, right? Yeah, that's yeah. And I'll talk about that as well. So a few remarks. First, the maximum probability of error criterion is sort of rudimentary, but on the other hand, it's eminently tractable. And there, of course, there are more discerning measures of privacy and also of recoverability. For instance, L1 distance or L2 distance between the user data and the querier's estimate of it. For instance, when you seek privacy. And these measures that I just mentioned serve to penalize the deviation of the querier's estimate of the data from its true value, which our approach doesn't. On the other hand, what I'm going to present here is eminently tractable, as you'll see. Now, there's, of course, a wealth of literature and prior work on privacy. There are several approaches. One of them is sort of I'm talking about information theoretic approaches, rate distortion like approaches. And then there's, of course, differential privacy. And I'll talk about it later during this presentation. And that looks at utility versus estimation, privacy versus utility or estimation. Of course, differential privacy is the reigning approach, is the dominant privacy approach today. There are also statistical approaches based on clustering, T-closeness, minimum mean square estimator, and also on cryptography, for instance, forward fully homomorphic encryption. I'll allude to it at the end of the talk. Now, our approach, as I mentioned earlier, has a few features which enable us to draw useful insights. So first, it's tractable, and we are able to get exact answers, even if some of the calculations are complicated and difficult. And one thing it does provide is an identification of optimal or asymptotically optimal row QR and their performance, and we'll see how this works. So let's start with characterizing the data privacy for a single query response. So data row privacy for a single query response. And of course, that also suggests that there can be multiple query responses, which we'll come to. So in all of this, the following, here are some preliminaries. So let's say this is the data set X. Here's a QBIS interpretation of a data set X. And then you have Z, which is the set of all function values. So let's say these are the data values. Let's say I is a specific data value. Now, I should also say in terms of notation, I'm going to use I to denote the function values, and sometimes little z, and I and j will represent function values depending on context. I might also use z, but I choose these symbols based on context, and they are all in the function value set. Now, if I look at I, then look at the inverse image of I under the mapping F. So here's I, and these are the set of values in X, which are mapped by F to the function value F. So I'm going to call this F inverse of I. And F inverse of I will play a useful role throughout the talk. And of course, if you take all the I symbols and you take the inverse images under F, then they're going to partition the X space, right? Now, here are a few preliminaries. A few terms that we'll use. So first, I'll denote by X star the maximum probability data symbol. So it's the argument that maximizes the probability of a symbol over all X in the data set. And then for I in Z, which is a function value, we'll define Xi star to be the local most probable symbol or maximum probability symbol. This is the argument that maximizes over all X in the inverse image of I, the probability of the symbol. And of course, we do this for every I in the function value set. A quantity that will be of interest is rho sub d. It plays the role of a critical value of rho. This is going to be defined to be the maximum probability among all data symbols divided by the sum of the local max probabilities, sum over I in Z of the probability of X I star. And it's easy to see that this thing is going to be less than 1, and also it's bounded below by 1 over k. Now, in fact, for each I function value, we can also write the probability of the locally most probable symbol, px star, as the px probability of f inverse of I, which is the inverse image of I under f, times 2 to the power minus h min of a probability mass function pi, where h min, this thing here, is the min entropy of, oops, sorry about this, min entropy of the probability mass function pi, which is defined as the probability of any symbol divided by the probability of the inverse image under I. And this is defined for every x in f inverse of I. So this is a probability mass function which is localized to the inverse images. And I mentioned this just to say that in the privacy literature, the notion of min entropy is very popular. And min entropy can be defined through the Renyi entropy of order alpha, but we won't get into it. I just wanted to mention this in passing. Now, so let's see, this is the notion of data privacy. What can we say about it? So here's data row privacy for a single row QR. Don't know why the pencil is acting up. Let me see. For a single row QR. So here's the Converse upper bound. And then we'll see if it can be attained. So for any row QR, let's call this W. If I look at 1 minus the probability, 1 minus pi rho of W, which is the probability of making an error under the row QR W, the errors made by the querier, this is the maximum probability of being correct. So this is the maximum over all estimators chosen by the querier of the probability of being correct regarding the data. So G of f of x is equal to x. And of course, this maximum is attained by the maximum a posteriori estimator, the map estimator. So this is going to be the probability that G map of W with respect to W of f of x is equal to x. And of course, this is bigger than or equal to the maximum probability among all data symbols. This is always true. We can all the map estimator can the estimator, the query can always declare the symbol to be the maximum probability symbol. So this is a simple, straightforward lower bound. And furthermore, the probability that the map estimator is correct is by definition the sum over all function values I in Z of the maximum over all symbols in the data set of the joint probability of the data and the function value or the estimate of the querier. So Px of x, W of I given x. Now, we can take the maximum over a reduced set, so sum over I in Z of the maximum over all x in the inverse image under I of px of x times w of I given x. But in this set, f inverse of I, w of I given x is by the by the recoverability requirement bigger than or equal to rho. So this is bigger than or equal to rho times the sum I in Z of px of xi star. Okay. And therefore we get that the that pi data rho, and these are lower bounds on being correct. So pi data rho, therefore, is straightforwardly bounded above by 1 minus the maximum of the two bounds that we had in the probability of being correct. So maximum of px of x star, which is the maximum probability symbols likelihood, and rho times the sum I in Z of px of xi star. And this can also be written as equivalently as 1 minus the maximum of rho sub d. The rho sub d, remember, was what we had defined earlier. Here was, sorry about this. Here's rho sub d. So coming back, I can write this as the maximum of rho sub d and rho, and then you have the sum over all I in Z of px of xi star. This is a straightforward converse upper bound on rho data privacy. Of course, the big question is, can this upper bound be attained? I should have said here, this is less than or equal to, because this is an upper bound. All right, now let me plot this as this upper bound as a function of rho. So if we were to do that, here's rho, here's this upper bound, namely this quantity here. And then we can see that it looks like this. It's straight, then goes linear, and then drops. Now, what are these points? So here is pi data privacy at rho equal to 0, which is 1 minus px of x star. And this is the map estimation error by the querier for the data value x without any observation. And then this point here is the rho d that we had defined earlier. And then this is the point where rho equal to 1. It means at this point, the querier is given the function value fully, and therefore pi data rho, pi data 1 at rho equal to 1 is 1 minus the sum over I in Z of px of xi star. Okay. And this is the map estimation error for x by the querier on the basis of a knowledge of the function value. So this is an upper bound on pi data rho privacy. And the question is there a scheme that will attain it?
Prakash,
yeah, sure.
So can you just give us some intuition again as to why the value at rho equals 0 and rho equals 1 should be tight? I think they should be tight. It's not just an upper bound.
No, so yeah, they will be tight. In fact, so what this says, you're going to see is that everything is tight. So when rho equal to 0, the best that the query can do, well, it gets no information, so it just picks the maximum value symbol to be its estimate of the data.
Yeah.
And then what happens at rho equal to 1 is it knows the function value, the query that is. If it knows the function value, it looks at the inverse image corresponding to that function value, inverse image in the x space, and picks the most likely symbol, right? That would be the best estimate for it. If it knew the function value, it would look at the inverse image in x under f of that function value, f inverse of this maximum probability function value, and then look for the maximum probability data symbol within that inverse image. And if you compute the error probability, that's what you'll get here, pi data 1. and it can be attained. Yeah. Okay. Now, in general, can this upper bound be attained? And so here is an achievability scheme. And before we get into the achievability scheme, I'm going to talk about something called an adnoise rho QR. So we have spoken of taking the data value X by the user and randomizing it directly. And then there's a special form of this randomization, which is for the user to compute the function value that is being sought and then randomize it before sending it to the querier. And that's what this adnoise rho QR does. It's an effective privacy mechanism. What it does is the output of the query of the randomization mechanism by the user is the function value f of x plus a noise, and I'm going to put this modulo k because the function value set is 0 through 0, 1 through k minus 1, where what is n? N is a z valued random variable. Z is the set of all function values, where n has the following distributional property. This conditional distribution of n, given the function value f of x, and x is conditionally independent of x. In other words, n satisfies this Markov property. So in effect, what this means is that the noise distribution, there's a conditional distribution for the noise given the function value, which means that the noise is tuned to the function value. And this is one of the advantages of doing things this way. The noise is not an independent noise, but it depends on the function value. And as a consequence of this, we get that if I look at the conditional distribution of n given the function value, well, this will lead to, because the query response is the function value plus this noise modulo k. This conditional distribution leads to a conditional distribution of the query response condition on the function value. And so finally, what you see is that if I look at the probability that the query response takes the value I, the output of the query response, given that the function value is j, and this is done for all I and j in the set Z, this can be defined by a stochastic matrix V of I given j. So this is a stochastic matrix, and this goes from Z to Z. V, which goes from Z to Z, it's a square matrix now, and all the diagonal elements V of I given I must be at least rho to satisfy the recoverability requirement. Now, so this is a special form of a query response. A question to ask is, when is a rho QRW, a general rho QRW given by the original stochastic matrix, also an adnoise rho QRV? And it's straightforward to check that if the rho QRW has identical rows for all x in the inverse image of I for every I under the mapping Z. In other words, if you look at the inverse image, if all the rows of W are identical, then this is tantamount to being an adnoise rho QR. V, which is a reduced size stochastic matrix from Z to Z. Remember that W was a stochastic matrix with R rows and K columns, where R is typically larger than K, where R is the size of the set of data values. And furthermore, the privacy is attained by the two for every row are the same. And this adnoise rho QR is particularly convenient. Now, going back to data privacy, we saw that this picture gave us an upper bound on data privacy. And in fact, it turns out that this is tight. So I'll state this and give you the query response that rho QR that attains it. So here's the first theorem, and it'll serve as the basis for what comes next. The theorem is data privacy or data row privacy, sorry. So for all values of a row lying between 0 and 1, the data row privacy is in fact equal to the expression that we had seen earlier, which is 1 minus the maximum of px and x star, which is the maximum probability among all data symbols, and rho times the sum over I in z of px of xi star. And of course, this is also equal to 1 minus the maximum of rho d and rho of the sum over all function values I of the maximum local probabilities in the inverse images, and is attained by an adenoise rho QR. Now here is the adenoise rho QR that attains it. So I'll state this as a proof, but it's not a complete proof. I'll specify the adenoise rho QR that attains this, and then the calculations are fairly straightforward. So achievability, we've seen the converse already. The achievability says that row privacy is attained by an adenoise by a query response f of x with values in z, and the matrix V, which specifies the adenoise rho QR, looks like this. So V, this is V, and it's a stochastic matrix from Z to Z, and here are the function values that lie in the set Z, and here are the corresponding query responses. So let's say we have the values from 0, 1, and let's say here's a generic J, and all the way through K minus 1. And then likewise, you have 0, 1. And then we have I equal to J, let's say. This is the diagonal element of V. And then you have another one here, which is I not equal to J. And then we have, of course, K minus 1. So these are all the symbols. Now, because if I look at I equal to J, my diagonal has not come out well geometrically, but this element will be the maximum of rho sub d and rho. And it guarantees that the stochastic matrix V at the diagonal value is at least rho. And this is when I equal to J, this point here. So this should correspond to this. And when I is not equal to J, the corresponding value here, ijth element, will be the remaining probability, which is 1 minus the maximum of rho sub d and rho. And then this remaining probability is distributed among all values of I here in a way, in a manner that is proportional to the corresponding px xi star. So multiplied by px xi star and divided by the appropriate term to make this a probability. So sum over all L not equal to J of Px of XL star. So again, the idea is that at the diagonal element, we put this quantity here to make sure that we have row privacy, which is at least row. And then the remaining probability, which is this difference, is distributed among all the i's in a manner that is proportional to the maximum local probabilities. And the denominator simply makes this a probability. Now, from here, of course, we can compute the V matrix. We know the V matrix here. And from the V matrix, we can compute the noise n that has to be added, namely this conditional distribution can be computed, given all these parameter values. Two things I wanted to say is that one is this optimal V that I've shown here is not unique in general. And furthermore, we see from the formula for the data privacy here that it is specified fully in terms, of course, of px of xi star, namely the min entropies. So any input distribution px, data distribution that has the same min entropies will have this row data privacy. So any questions at this point? No? Can you hear me?
Yeah, I can hear you. Are there any questions?
Thank you. Yeah, question. Yeah.
Yeah, just a high level question about what is going on here. So, at least in differential privacy and so on, I mean, when you fix a function little f, you have like a sufficient statistic that is, the sensitivity of the function that allows you to add noise in such a way as to at least ensure privacy without row recoverability.
Mm-hmm.
Right? So here, is there any such sufficient statistic of some sense that is, you're working with the F inverse kind of sets,
Yeah.
right?
Yeah, that's the
that's
the answer to the question. Yeah. So in differential privacy, the noise that is added has a level that depends on the sensitivity of the query function, which of course is defined as the maximum separation in function values corresponding to proximate data vectors, right? This function sensitivity in general can be unknown and can be large as well, and that would govern the level of noise we have to add. So here things are being done. Here, this method of add noise, this particular form of it is resilient to function sensitivity because we create a conditional distribution of the noise given the function value. And in effect, the function value acts as a sufficient statistic.
Yeah.
Okay. Yeah. Okay. All right. So now we go to data privacy for multiple row QRs. In the first case, we saw that privacy had this simple form, as this picture showed. This of course, this upper bound is also tight. That the initially the data privacy is such that the query gets no help from the query response. That's this flat region that you see, and then at this point, the query knows the function value, and this corresponds to the probability of the map estimator knowing the function value, and then there's a linear drop. Now, the natural question is, what happens if the query demands multiple query responses for the same data value? And that problem becomes a little more interesting. So if you look at data privacy for multiple row QRs. Okay. So now the query seeks to recover f of x, the function value, from multiple row QRs. And those row QRs are f1 of x through fn of x, all for the same data value for any finite value of n. Okay? And we're going to assume that the row QRs that are provided by the user, so f1 of x through fn of x, we're going to assume them to be conditionally mutually independent, conditioned on x. They're not necessarily IID, for instance. And there's going to be a stringent recoverability requirement. So each FT of X, each query response, FT of X, must be a row QR. In other words, it must satisfy the recoverability requirement. And this is a usual feature. This is an unusual feature in the privacy analysis. There's a deliberate bias against the user so as to make for a conservative or a diminished extent of privacy. So the query is favored. Now, why multiple row QRs? So this formulation is appropriate when the main objective of the query is, for a given value of row, is to improve estimation accuracy beyond row, because each query response meets the row recoverability constraint. But when they are strung together, multiple query responses, the recoverability can be at an accuracy level that exceeds row, as we'll see. So the main objective of the query is to improve estimation accuracy beyond row for a given function f of x by soliciting multiple row QRs, or we can also view this as n queryers in a multi-party setting, each of whom seeks a row QR. And then all these queryers collude and pool their row QRs that they've received from the user to get a collective estimation accuracy that exceeds row. And in doing that, they also degrade data privacy. On the other hand, the user designs these row QRs to maximize privacy of the data X. And this sort of analysis is often referred to as composition analysis in the privacy literature, which means that the querier is given additional resources or benefits, and the idea is to see how a composition of all these benefits that are afforded to the querier, how they degrade corresponding data privacy. So now, how do you define data privacy? It's much like what we saw earlier. Now, data row privacy for multiple row QRs is going to be defined in a similar manner. So this is going to be pi data for n query responses of a row is the maximum privacy attainable by row QRs ft of x, t going from 1 to n, these multiple row QRs. And the definition is that this is the maximum of pi row of W1 through Wn. These n row QRs F1 through Fn can also be represented by stochastic matrices W1 through Wn. And the maximum is taken over all W1 through Wn, which are chosen by the user, but each of them has to satisfy a row recoverability constraint. So f of x given x should be big, at least row, and this is true for all x in the data set. Okay, so this is the definition of data row privacy. Now, it's clear that as the querier gets more query responses, privacy is going to degrade, and in general, estimation accuracy by the querier using n query responses can go beyond row, can go above row. Now, this quantity here is also represented, can also be written as pi row of f1 through fn. And this is, in effect, pi row is the one that minimizes the probability of error for the querier given w1 through wn or f1 through fn. So this is the probability of the map estimator of x on the basis of f1 of x through fn of x. Now, this can also be written equivalently as the probability of the map estimator, which of course will depend on w1 through wn, to compute the joint probability of the data symbol and the query responses on the basis of z1 through zn. So z1 through zn are the same as f1 of x through fn of x, and the probability of error, which is the probability that this is not equal to x. So as I said, I'm going to use Z1 through Zn also to represent F1 of X through Fn of X, and they all take values in the set script Z, the function value set. So here's the characterization of data row privacy. So this is data row privacy for multiple row QRs. Now, if you have multiple row QRs, certainly with increasing number of row QRs, the querier can eventually estimate the function value with large probability. In the case of a single row QR, we characterize data privacy for different values of row. In the case of multiple row QRs, even for a value of row which is strictly smaller than 1, in the limit of multiple row QRs as n tends to infinity, the querier has a chance to estimate the function value f of x in the limit. And therefore, the converse for data privacy says the following: for a row lying between 0 and 1, and for all values of n, the data privacy by data n of row, well, is less than or equal to pi of 1. Pi of 1, remember, recall, is the best data privacy here when you had a single query response and the querier knew the function value. So now the querier for a general value of row doesn't know the exact function value, but it has multiple row QRs. In the limit, it will estimate pi of 1. Now, for finite values of n, of course, it will not have pi of 1, and so there will be more privacy than pi of 1, and that's given by an upper bound, this quantity determined by this quantity gamma n of row. That is the upper bound. So it can exceed pi of n, 1, but not beyond pi n of gamma n of rho. And the achievability says that for high values of rho, interesting values of rho bigger than 0.5, so rho strictly bigger than 0.5, and of course less than 1. And for all values of n bigger than 1, the data privacy of rho is bigger than this limit pi of 1 plus a quantity lambda n of rho. So in other words, data privacy lies between a band around, in a band around pi of 1 plus gamma n of rho, and the low bound is pi of 1 plus lambda n of rho, where for significant values of rho, about 0.5, which is also the interesting zone, these two deviations, limit of n of gamma n of rho and lambda n of rho, tend to 0. And they do so exponentially fast. So exponentially rapidly with an exponent which is approximately the Kullback-Leibler divergence between a Bernoulli random variable, a perfectly random bit, and a Bernoulli row random variable. And of course, because rho is strictly bigger than 0.5, this divergence is positive. Now, therefore, what we see from here is that for rho in the region from 0.5 to 1, the limit in n of the data privacy is equal to pi data of 1, which we saw earlier. So I should say here data maybe. And this, in effect, is the map estimation error for x when the query knows the value of the function f of x.
Prakash, one
Sure.
silly. So when rho equals 0, what happens? So when rho equals 0, you have no constraint on the entries of your W matrix. So you're essentially just looking for the probability that the map estimator is going to get something wrong. After
Yeah,
entering.
the row equals 0, no information really is provided to the query, and so the best that the query can do is to pick the maximum value symbol, right?
That is for one.
Yeah, for 1 and also for n, it should not vary. So really, in the limit, this gamma n and lambda n go to 0, and then you look at pi data 1, which becomes pi data 0.
Right.
Yeah, so you can't do any better than that.
Yeah.
Yeah. I'm skipping some of the details. Yes, but those what I just mentioned can be seen through a straightforward calculation. Yeah, and of course the interesting in an
One more
application.
question, Prakash.
Yeah. Yes.
I'm assuming that you should be able to do better if you allow for adding correlated noise across queries, right?
If you allow for well, in fact, there's noise.
So somewhere
In
in
general, no. Sorry. So in general, the formulation allows the WTs to be different. That's number one. So it needn't be stationary. And number two is that we are taking them to be mutually independent condition on X. So if you look at the FTs themselves without the conditioning, there will be correlation among them. Now,
I mean, I'm assuming, suppose you just give the same response to every n.
I'm sorry, say that again.
Suppose you give the same response to every n.
Yeah.
Right. So in that case, the query wouldn't have any more information than the n equals 1 case.
That is true. Yes.
Right. So
Yes.
that should allow you to, in some sense, do better than
yeah.
power get here.
Yeah. Yes. So the thing that is right. So of course you will no longer have the conditional independence property also, right? Because all the Fs are the same. Now, in all these analysis, the spirit is to give the query as much leeway as possible, right? And then see what happens to the data privacy. So in other words, the formulation is biased in favor of the query and against the user to see what is the worst case privacy from the user standpoint. And that's what this analysis does.
Okay.
Yeah. Okay. Yeah. So that's why there is a requirement. So if you look at the W's are required to satisfy this conditional mutual independence.
Right. So I mean, is that the same as saying that, for every n you add an independent noise?
For every n, no. So for every n, the noise itself may not be independent because the noise has to be. If you were to use an add noise scheme, then the add noise scheme would have to be the noises would have to be conditionally independent.
Right. Of the past.
Yeah.
Okay.
Yes.
Okay.
So yes. Now, I don't know how much time do I have at this point?
About 10 minutes, 10, 15 minutes. Yeah.
10, 15 minutes. Okay. So then I'm going to have to skip a lot of what I wanted to say, which is okay. So let me do one thing. I wanted to, what I'll do is I'll give us a brief proof of the Converse result, which is due to Rohit Premlal, and I'm presenting it here with his permission. I'll give you the idea of the Converse proof, and then I'll sort of do a summary of what I wanted to talk about, and then we'll stop. Yes. So first of all, the Converse. In fact, what I wanted to say before that is that the map estimator for the data when rho is bigger than 0.5 can estimate the function value with probability 1 as n tends to infinity, as this remark says. Now, coming to the converse result, which is this one here, the original converse that Ajay Nageshwaran and I had some intricate counting arguments, and then Rohit Premlal, who's doing his PhD with me now, showed me recently a very elegant proof which gets to the answer directly. And so, with Rohit's permission, I'm going to present his converse next. It also shows some of the techniques that can be used. So, proof of, this is, yeah, converse proof. And the idea is as follows. And this is due to Rohit Premlal. It's a recent proof. So recall that the data privacy n with n query responses at row is defined to be the maximum over W1 through Wn, over the choice of W1 through Wn, with each of them Wt of f of x. So W can depend on T. This has to be bigger than or equal to rho. And this is true for all x in the data set. And you look at the probability of the map estimator by the querier based on W1 through Wn. Given the data Z1 through Zn is not equal to x. All right, now, if the querier were to use a suboptimal estimator, and this is Rohit's idea, then the probability of error would be no smaller. So this is the probability of G tilde, of the estimator G tilde, based on Z1 to Zn not being equal to x, where this G tilde is suboptimal. And this is true, of course, for any suboptimal estimator in comparison with the optimal map estimator. And the question is how to choose the suboptimal. And so here's Rohit's suboptimal estimator. Given the data values, fixed data values, Z1 through Zn, let's say, all in Z, the suboptimal estimator has two steps. So step one is the query finds an estimate of the function value. So estimate the function value f of x equal to I on the basis of Z1 through Zn in the following way. So I hat, which is the estimate by the query of the function value, which of course will depend on Z1 through Zn, is the argument that maximizes over all I in Z the counts of the various Z's. So sum over T going from 1 to n of the indicator function that Zt equal to I. And the querier declares an error if the maximum is not unique, if the argument max is not unique. So this is a simple estimator which looks at Z1 through Zn and picks the symbol, the function value symbol that occurs most often, and declares that to be a function value. Now, in the second step, what the querier does is it finds an estimate of the data value given Z1 through Zn. And what it does, in effect, is x hat of Z1 to Zn, which is the estimate of the data value given the query response is Z1 through Zn. It looks at the probability of the symbol x in the inverse image under the function value that it has just estimated. So it's argument over max of x in f inverse of I hat. And this, of course, i.e., this what the suboptimal estimator does, G tilde, in estimating the data value on the basis of the query responses Z1 through Zn, is the argument that maximizes over all x in f hat inverse of I hat. Oh, sorry, this is too many hats. One must never wear too many hats. So x in f inverse of I hat of the probability of a symbol. And then compute the probability of error. So clearly the probability of error for the optimum estimator is no smaller than the probability of error of the suboptimal estimator. And if we can get that, we can get an upper bound on data privacy. So this thing, then we can proceed as follows. The probability that G tilde, the estimator, on the basis of Z1 through Zn, the random query responses, does not produce the data value accurately. Now, is the probability just by the law of total probabilities? This is G tilde of Z1 through Zn not equal to X, and the event that X lies in the set Xi star of locally most probable symbols, I and Z, plus the probability of error by this estimator, Z1 through Zn, not equal to X, given that X lies in the complementary set, which is script X, the set of all data values, minus the set of these maximum probability symbols. Now, it's a straightforward calculation to show that this probability here, the second term, is bounded above by 1 minus the sum over all function values of the maximum probability symbols. And this, of course, as you've seen before, is pi data 1. So therefore, we now get that this expression is equal to, or I should say less than equal to, the sum over all I in Z. Let me do this. Sorry about this. Here. Is less than equal to the sum over all I in Z, all data values, Px of x star star. So I'm looking at the first term now, and then look at the probability that the suboptimal estimator doesn't get the maximum probability symbol correctly, condition on the value of the maximum probability symbol plus pi 1. And then we look at this term here. The event that, the error event, G tilde of Z1 through Zn is not equal to Xi star, is the same as the event that in the first step, the estimate of the function value was not equal to I. And therefore, we can go back to this expression here, this part, and write this as the probability that I hat of Z1 through Zn is not equal to I, given that the data takes the corresponding maximum value symbol. And it's then straightforward to show that this is the sum over all t going from 1 to n, because of this observation here, that the indicator function, that zt is not equal to I, summed over all possible values of t going from 1 through n. This is, I'm sorry, I got, yeah, this is right. This is bigger than or equal to n by 2, given that x equal to xi star. And then use a Chernoff bound appropriately to conclude that this is bounded above by a constant that depends on k, the number of function values, times x minus n, the divergence, Kullback-Leibler divergence between Bernoulli 0.5 and Bernoulli rho. And that's the proof. So it's a direct converse. Now, I'll just mention the achievability part. How do you achieve this data privacy for n row QRs? Now, here's a simple privacy mechanism, V, which is an add noise mechanism in the region where rho lies between 0.5 and 1. And it looks like this. So here's a simple mechanism. So here we have V, and let's take the case where K is even, the number of function values. Then you have 0, 1, all the way through K minus 1, and 0, 1, all the way through K minus 1. The rows represent the function values, and the columns represent the values of the query response. So the diagonals have to be at least row. So put this to be row, this to be row, and the rest to be 1 minus row here, 1 minus row. And the rest are all zeros. So we have these block diagonal matrices of size 2, and they all are row, 1 minus row. And everything else is 0. I'm sorry, this is row. Sorry about this. For some reason, my iPad pencil is acting up today, which it shouldn't. And then row, 1 minus row. And likewise, row, 1 minus row, 1 minus row. And it turns out that this attains the best row privacy. In fact, as you see, this is a very simple privacy mechanism, add noise privacy mechanism. It does not depend on the probability of the data, px. Now the question remains, if the choice of V were to depend on px, perhaps we could get a better performance in terms of data privacy, in that it approaches the limit faster. The proof of this is rather complicated, and I'll omit it. Now, I think we are running out of time. Is that correct, Arvind? Hello.
Yeah, we're almost done. So as far as time is concerned,
so let me say a few words. Now, I wanted to say a few words. There are other notions of privacy. So one is I had an ambitious program here. So first is predicate privacy, where as compared with or in contrast with data privacy, we want to safeguard some attributes of the data while releasing others. So now privacy is assessed not for X, but for some specified attribute H of X, let's say, of the data. And this is a more stringent form of privacy, because if you can make H of X secure, then of course we can make X itself, the data, at least as secure. And it turns out that we can analyze this in terms of what we've just seen. Then there is the notion of list privacy. So I remember that I was discussing this result with Himanshu Tyagi once, and he looked at this V that you see in front of you, in green, with these block diagonal row 1 minus row matrices. And he said, yes, it gives you data privacy, but if the query were to form a list of size 2, then the user would be in trouble. And so that led to the notion of list row privacy, where privacy is assessed by the estimate of the query being a value, data value that is not of size 1, but it lies in a list of, let's say, size L. So privacy is assessed as list privacy, where you're looking at the probability that X does not lie in a query's estimate of the data lying in a list of size L. And of course, this is a more stringent form of privacy, because if you can make list privacy to be large, then of course data privacy can be at least as large. And this guards against winnow and conquer strategies. Then there's a notion of anti-collusion privacy, which Rohit is currently studying. Here, the user provides separate predicates of the data, for instance, medical information, financial information, etc., to multiple queries, who may then collude to impair data privacy. And in all of these problems, general questions are Are there better means, better measures of privacy than these error probabilities that I've mentioned, although they are very tractable? Can we compare the performance of ad noise row QRs versus general privacy mechanisms that depend on general stochastic matrices W? Then there is the notion of linkage privacy, which Himanshu Tyagi introduced me to a couple of years ago. And in work with Himanshu, Aditya Singh, his former student, Rohit, we formulated the notion of linkage privacy in this framework that we've just seen, along in the same spirit. And here it is required that a third-party application, a TPA, with access to data associated with multiple users through releases by several separate servers, should not be able to link records that came from the same users. An example, for instance, is in graph matching, where the structures of social networks such as Facebook and X are correlated, since the same users are likely to connect among themselves in both networks. So a shared advertising agency, which is a third-party application for both networks with access to their social graphs, should not be able to link the accounts of the same user in the two networks. Then, of course, I wanted to talk about the notion of differential privacy, which we won't, and also, finally, the notion of distribution privacy. What is distribution privacy? This is a new notion which aims to capture privacy of a game theoretic flavor. So the question is the following: how must a user devise a probabilistic strategy or an algorithm or a policy that is to be guarded while revealing associated actions to a querier who can learn adaptively? So potential futuristic applications: an AI-driven financial trader who reveals trading preferences through daily bidding actions. So this is the recoverability of function, a recoverability requirement of function values. But this trader seeks to guard the workings of an underlying probabilistic algorithm, for instance, which is distribution privacy. Or you have IoT sensors that must recover user commands for execution. That's function recoverability, but without the details of user habits being compromised. Right? And a cosmic interpretation that I like is: what mechanism must nature choose in order to generate its secrets that makes it hardest for a mortal querier to fathom from a variety of measurements? So this is a game theoretic formulation, and it involves Kullback-Leibler divergences, which can also be replaced in general by F divergences, by Remy divergences of order alpha, and really these formulations lead to an interesting class of problems. And also, these problems, this problem formulation can be connected to local differential privacy, which I did not define, by requiring the stochastic matrix W, or the privacy mechanism, to satisfy, in addition, a differential privacy or a local differential privacy constraint. And finally, a fully homomorphic encryption. So this is a cryptographic approach that promises to become a definitive solution in information privacy. So FHE, or fully homomorphic encryption, allows the value of a function to be computed directly on encrypted user data without revealing the data itself. And complex cryptographic techniques are under development that rely on algebraic methods that are computationally expensive. And so this will need several years of innovative experimentation in order to identify the right methods. Meanwhile, alternative approaches, of course, alternative approaches are needed to solve privacy problems or confront privacy problems, a new generation of them, especially in multi-party environments that either confront us or loom on the horizon. And so, in closing, coming to our approach, it's new and the formulations are rudimentary. They make for analytical tractability, and as you saw, the analysis is based on first principles from probability theory, information theory. This approach of ours does yield useful insight, but also suffers from some of the shortcomings, at least one of which I alluded to. And one advantage is that it's a framework that enables links to differential privacy and local differential privacy. And importantly, it raises many interesting open questions, especially in multi-party settings. So with that, I shall conclude. Thank you.
Thanks, Prakash.
Hello.
Very, it was a very nice talk, especially we appreciate the effort that you took to actually derive things from scratch, and I'm sure everybody took home something from this
Thank you.
presentation. Thanks again for your time and for making it here despite all the circumstances and everything.
Thank
So,
you.
yeah.
Thank you again for your kind invitation. I'm sorry I had to postpone the talk, but I'm glad I was able to present it here today. I do regret the fact that I chose a very ambitious agenda, a number of things that I wanted to talk about, but this format, as you said, it's something that I like very much. It enables one to proceed at a pace that is consistent with that in a classroom, but then of course it limits the scope of presentation. But I think that is just as well. Thank you again.
Thanks, Prakash. Yeah, we'll send you a link to the recording. I think you already have the link to the recording, so you can.
I do. Thank you.
Thanks again. Yeah.
Thank you. All the best. Yes.